We are starting our last unit in Math 2, which is on probability, and you have probably learned about probability before, but we're going to add on to what you know probably. And this unit is going to be very different from all the others. It's more statistics-based. What is probability? Probability is finding the chances of something happening, or like how likely it is that something happens. The thing that we are trying to calculate the probability for is called an event. And the probability is written P parentheses event. So for example, that might be like something like this would be the probability that it will rain, or the chances that it will rain. That's how it is written. The rain would be the event. Probability will always be a number between 0 and 1. 0 would mean it is definitely not going to happen, and 1 would mean it is definitely going to happen. Or it might be written as a percent or a fraction. So number 1, if we have a probability of 9/10, what would that mean? Well, that's if we're looking at between 0 and 1, 1 would be definite. So 10 out of 10 would mean it's definitely going to happen. 9 out of 10 is still very likely. So we would say that number 1 is D, because 9 out of 10 would be 0.9, which is pretty close to 1. Number 2, which could not be a probability if probability is always a number between 0 and 1. 0.8 is between 0 and 1. 32% is the same as 0.32. That's between 0 and 1. However, 6/5, that's the same as 1.2 because it's bigger than 1 because the number on top is bigger. So that is not a probability. It's not possible to say 6/5 is the probability, and 1/3 is between 0 and 1. Now we're going to look at the complement of an event. So the complement is all other possible outcomes. For example, if we looked at the probability that it will rain, the complement of that would be the probability that it will not rain. And the event and its complement, if you add their probabilities, it will always be 100%. So basically the probability that something will occur and the probability that it will not occur will add to 1. So for example, the probability that Hunter will fail his statistics test is 0.32. What's the probability that he will pass? So passing would be the complement of failing. And since that's the complement, they would need to add to 1. If there is a 32% chance he will fail, what is the probability that he will pass? That would be 68% chance. So the complement, a probability of an event, and the probability of its complement would add to 1, which is the same as 100%. Now, number 4, we're looking at the dropout rate for undergraduate students is 40%. It says, which is another way to represent this statistics. So we can write that obviously as a decimal. What would 40% be as a decimal? That would be 0.4 or 0.40. We could write it as a fraction. And percent literally means per 100, or out of 100, so I could do 40 divided by 100. 40 out of 100 is the same as 40%. So that's another way to write that. And obviously we could reduce 40 over 100 if we divided both of them by 2 or even something bigger than 2. So let's figure out if any of these have the same value as 40%, 0.4, or 40 out of 100. Which one of these would that be? Letter A, about 2 out of every 5 undergraduate students drop out. We would need to see if we reduce this fraction if it equals the same thing as 2 out of 5. If you do not have a calculator, we should know that you could divide both of these by 20. And if you do that, it does give you 2/5. So 40% is the same as 2/5. That's why that's the same as saying 2 out of every 5 drop out. Remember, if you do have a graphing calculator with you, you can change a decimal to a fraction or reduce a fraction by pressing Math, Enter, Enter to put a fraction in simplest form. Okay. For letter B, you could reduce 140 out of 250 to see if that is equal to 0.4 or 2/5, but it would not be. 2/7 is obviously not equal to those. And letter D, 4 out of 100 is also not equal to 2 out of 5. That's far less. All right, now we're going to actually calculate the probability. We're going to be calculating first what's called the experimental probability, which is using actual data from the real world, trials or experiments. So this is using actual data from actual experiments. Michaela owns a small business, and last week, 58 customers paid cash, 25 used a debit card, and 2 used a credit card. So we're going to look at those numbers. Express the probability based on these results that the next customer will pay with a debit card. So to find the probability, we find the number of ways that the event happened divided by the total number of trials. So what is the number of ways that, or the number of times that somebody paid with a debit card? So 25 is the number of ways that they paid with a debit card. How can we find the total number of people? For that, we would need to add 58 plus 25 plus 2, and that would give me 85. All right, so 25 out of the 85 total paid with a debit card. So then what is the probability? I don't see that in any of the answer choices, so I would need to reduce this. Remember, you could press Math, Enter, Enter on a graphing calculator, or you can divide both of these by 5, and that would give you D. Let's do another experimental probability. We're looking at the probability that a student will play the guitar as a decimal. This time we're going to put a decimal. So let's look at the total number of students, so the number of ways the event happened. So we could look at this many guitar players. So how many guitar players were there total? That would be 20. Okay, and then we need to divide that by the total number of people surveyed, or the total number of trials. I would need to add all of these up. So see if you can add those up and then divide to find the probability. If I add all these numbers up, I got 70. So 20 out of 70 as a decimal is 0.29. Okay, one more like that. A spinner is divided into 5 sections. They're not equal sizes, so it's not equally likely that you would get each color. It's spun several times, and this tells us what it lands on. What's the probability that the next spin will land on yellow? So we're looking at using the experiment. So we need to find the total number of yellow out of the total number of trials. And what do you get? There were 3 times that it landed on yellow. Total, we would need to add all of these up, and those should add to 38. And then 3 divided by 28, if we look at a decimal to the nearest hundredth, would be 0.08. Now we're going to look at what's called the theoretical probability. So we just looked at experimental probability, which is using actual data from an experiment. But the theoretical probability is where you're not using actual data, you're just thinking about theoretically what are the chances. And for example, an example for that might be flipping a coin. If you flip a coin, theoretically, the chances that you would get heads is 50% and tails is 50%. So that is theoretical. We are also going to use a deck of cards a lot to find theoretical probability. Okay, number 8 says, what is the probability of drawing a spade in a standard deck of 52 cards, theoretically? So we would need to do the number of ways you could get a spade divided by the total number of possible outcomes. If you draw a card, the total number of possible outcomes in a 52 card deck is 52. And what is the number of ways of getting a spade? That would be 13. So really, I mean, these are very similar. It's just the wording is a little different. But the theoretical means you're saying what could happen, what would be most likely without actually testing it out. So, looking at the answer choices, which of those would be the same as 13 over 52? That would be 0.25. That's the same as 1/4. And that makes sense because 1/4 of the cards in the deck are going to be spades. That's a theoretical probability. Okay, let's look at another theoretical probability. Grace received an invitation to an event and she has to choose an appetizer, main course, and dessert. This is the menu. What is the theoretical probability that she'll choose the house salad, lasagna, and brownie? And the thing that's going to be a little bit difficult with this one is trying to find what's called the sample space. So that's finding all of the different combinations of meals that you could choose if you have 2 appetizers, 3 main courses, and 2 desserts to choose from. One thing that can be helpful is to make a diagram, a tree diagram, and start out with, let's say you choose for the appetizer, you could choose the house salad or the soup. And then we go from there and we look at the options for main course. You could choose the chicken parmesan, you could choose the fettuccine alfredo, or you could choose the lasagna. So this is called a tree diagram, listing out all of the possibilities for sample space. So far, if we follow one branch of this tree, like if I went here, that would be soup and fettuccine alfredo. Okay, and then we would, of course, add on to that all of the dessert options, which would be the cheesecake and the brownie, and we would have all of these possibilities as well. So this is listing out what's called the sample space, which is the number of total choices, basically, that you could choose from, because we want to know how many possibilities there are for the bottom of my fraction there. Okay, so again, you could choose soup, chicken parmesan, and a cheesecake or brownie. You could choose soup, fettuccine alfredo, and a cheesecake or brownie. Okay, this is listing out the sample space using a probability tree. So these are all of the number of possibilities. If we follow each branch of the tree, that is a possibility. House salad, lasagna, and brownie. This is the one we are looking for. House salad, lasagna. So see if you can figure out how many combinations there are to choose from. The probability would be 1/12 because there are 12 branches of this tree ultimately, and house salad, lasagna, and brownie is one of the 12 branches. Now, let's see if we can find a shortcut to get that 12 if I know that there are 2 of one item to choose from and 3 and then 2. How many branches would be on the tree instead of listing it all out like that? What could you do to get to 12? Hopefully you notice that you could do 2 times 3 times 2, and that would give you 12. Let's see if we could do the same thing for this one. Miss Maple's 3rd grade class is having an ice cream party. There are 3 different flavors of ice cream, so we would have 3 different flavors. There are 5 different kinds of sprinkles, and then we have chocolate or strawberry syrup. So there's 2 different, and I don't know why I wrote a 2 when that should be a 5. And there are 2 different types of syrup. Okay, so you could make a tree to find all the possibilities, but we want to figure out if you choose vanilla ice cream, chocolate sprinkles, and chocolate syrup. So choosing one of each of those. Do you know what that probability would be? The number of combinations we could do would be 3 times 5 times 2. 3 times 5 times 2 is 30. And that is one of the possible combinations out of 30 combinations. If you do 1 divided by 30, that gives you about 3.33%. That is a theoretical probability, not an experimental probability, because we don't have actual data to know what the students like and that kind of thing. All right, and another one. If you flip a coin 3 times, what's the probability of getting tails all 3 times? So if you flip a coin, the first time you flip a coin, you could get heads or tails. Okay, then you could flip it again and again get heads, tails, heads or tails. So this would be heads, then heads, heads, then tails, tails, then heads, tails, then tails. And then you're going to flip a coin the 3rd time. So theoretically, think about how many combinations there would be and what the probability would be. So again, you could list out all of these possibilities, and there would be 8 possibilities. We're looking at getting tails all 3 times. That is one of the 8 possibilities that you would get tails, then tails, then tails. So now let's look at comparing the experimental and theoretical probability. Experimental, again, is using actual data from experiments. Theoretical is just assuming what the probability would be based on the numbers and chances that we know. We have a 6-sided cube rolled 100 times, and the frequency for rolling a 3 is 20. So let's look at the experimental and theoretical probability. Experimental means we're looking at what actually happened. They rolled a coin 100 times, and they got a 3 20 times. Theoretically, if you roll a fair coin 100 times, and there are 6 sides, and it's fair, that means they're all equally likely. That means that 1 out of every 6 theoretically should have a probability of getting a 3. Okay, so theoretically, 1/6 would be the chances of getting a 3. But actually what happened was 20 out of 10. Okay, so this is the experimental, this is the theoretical, and of course they reduced it in the answer choice to see if you could figure out what the answer would be. Theoretically is 1/6. Experimental, if you reduce that, is 1/5. Now, let's do another one like that. Another cube that is rolled 54 times. So if you roll a dice 54 times, theoretically you should get a 6. Theoretically you should get a 6. Let's figure out how many times. If you roll, the probability of getting a 6 is 1/6, theoretically. And if we did that 54 times, that would tell us that you should get 9 times out of 54 that you should roll a 6. But actually what happened was 3 out of 54 times was the experimental probability. So let's think about if that is consistent, meaning is that close to the theoretical probability? Well, let's look at the answer choices. No, because the theoretical probability says it should land 6 times. No, because it should land 9 times. We know they're not the same. And I don't even know what that one's saying. So the answer to this one would be it should land on a 6 9 times, theoretically, if you roll a dice 54 times. But this was only 3 times. So they're not always going to be the same because experiment is what actually happens. Theoretical is what we would kind of guess would happen. Okay, let's look at this one to see if they are consistent as well. The difference between experimental and theoretical. Daryl rolled 2 dice labeled 1 through 6 36 times, and he calculated the sum of the 2 dice. What does the sum mean? Sum means we add what you would get. He had 4 of the 36, so this is the experimental probability, was that 4 out of 36 of his rolls had a sum that was greater than 8. Now we need to find the theoretical probability of rolling a sum greater than 8. So we need to think about all of the ways that there are to roll 2 dice that add up to something bigger than 8. So we're going to list out all of the possible sums. I'm going to put the possibilities, if you roll a 1, 2, 3, 4, 5, or 6 for the first dice, and a 1, 2, 3, 4, 5, or 6 with the second dice, and we're going to look at the sum. If you roll a 1 for both die, 1 plus 1 is 2. Okay, you could roll a 1 on the first die and a 2 on the second die. That would give you 3. So basically you're going to add 1 to all of these, okay? Then we're going to do the same thing but add 2 to all of these. See if you could fill in the rest of this table to figure out the total number of sums that you could get when you roll 2 dice, and figure out how many of them had a sum greater than 8. If you fill in the rest of the table, the sums greater than 8 would be all of these right here. Those are all greater than 8. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possibilities for getting a sum greater than 8. And that would be out of, if we figure out how many of these there are, how many possibilities are there? There's 36 possibilities. That just happens to be the same as this 36, but that's just a coincidence. There's 36 possibilities because 6 times 6, there's 36 numbers here. All right, so he got a sum greater than 8 4 times, but theoretically there are 10, the probability is 10 out of 36. So which one of these would be the answer? The answer for this one would be C, because theoretically it should be closer to 10 times that you would get a sum greater than 8, but experimentally it was 4 times that it happened. Something else that you need to know is that the more trials there are in an experiment, the closer the experimental probability gets to the theoretical probability. So that kind of makes sense when you think about it. If we know that the theoretical probability of flipping a coin of getting heads is 50%. Let's say you flip a coin 3 or 4 times. It's probably going to be pretty far from 50% of the times that you're going to get a heads. However, if you were to flip a coin 5 million times, which is possible to do in something called a simulation, chances are it's going to be very close to 50% of the times because you have a lot of trials. A simulation is a substitution for an experiment using actual objects. That could be a computer model. There are tons of computer simulations out there that roll several coins or dice or something like that. And you could do that to find the probability for something that can't be easily modeled. For example, let's say we wanted to predict the gender for 10 babies. And we know that the probability of male and female is 50%. It's the same thing with flipping a coin. So we could set up a simulation and flip 10 coins to predict the gender of 10 babies. That's an example of a simulation. And in a simulation or in an experiment, the more trials there are, the closer the experimental probability gets to the theoretical probability. So, a spinner is divided into 4 equal sections, green, red, yellow, and blue. This shows the number of times the spinner lands on each section. So in the table are the results from the experiment. Theoretically, if we're spinning something that has 4 equal sections, if they're all equal, then what is the theoretical probability of landing on one of the sections? 1/4. Okay, so theoretically, 1/4 is the probability for getting, say, green or red or yellow. And so let's figure out how many times they were spinning the spinner here. I would need to add all of those up, and we would find that there were 25 spins here, which isn't a whole lot, but it is quite a bit. So if there were 25 times of spinning the spinner, and the probability is 1/4, then about how many times would we expect it to land on each color if they are all equal? Well, that's about, if we divide 25 by 4, that would be about 6.25 times theoretically that it would land on each of them. Obviously, you can't have a 0.25, so that's why this is just theoretically. So the experimental probability for green was 5 out of 25 and 8 out of 25. For yellow, it was 6 out of 25, and for blue, it was 6 out of 25. So does that mean we should use? So basically, we want to look at the difference between the experimental and theoretical probability. And if there is a big difference between them, then something's not right, meaning like, okay, this is not actually a fair spinner because it's landing on one more than the other. So let's take a look at the answer choices and figure out if this should be questioned. And looking at these answer choices, see which one you think that would be. So it says letter A should not be questioned because they match the theoretical probability matches the actual experimental probabilities. They do not match. They're not exactly alike, and it's not possible for them to match because you can't have 6.25 times of it landing on something. Letter B, the probability should not be questioned because the results in the table are close enough given the number of trials. I'd say that that would be accurate. The more trials, if they would have done this spinner 500,000 times, chances are it's going to be a lot closer to 1/4 of the time. Okay. Letter C, they do not match. So, and if they match, we would not need to question them at all. And D doesn't make sense either. All right, number 16, a student used a random number generator to simulate rolling a cube 30 times. So this is basically like a computer model. And these are the numbers that they got when they rolled the cube 30 times. The theoretical probability of rolling a fair cube, the probability of rolling a 1 is 1/6. Obviously, there's a 1 in 6 chance that you're going to roll a 1, theoretically. But the experimental probability using the simulation, this says that it was a 1 out of 15 times. In other words, they rolled a 1 twice out of the 30 trials. So twice out of 30, that's where they got the 1/15. So why do you think that they were not consistent? This would be that there were too few rolls of the number cube. So if they would have done this, you know, a ton of times, if they would have rolled the cube 1,000 times, it probably would have been a lot closer to 1/6. You would probably get a 1 a lot more. So the more trials, the closer the experimental gets to the theoretical probability. Okay. Kim tosses a coin multiple times, records the outcomes. Which statement is always true? See if you can figure out what that would be. So for the first 2 tosses, we don't know exactly what the experimental probability would be. We know what the theoretical would be, but not experimental. She could get 1 head and 1 tail. Then that would be a 50-50 chance for each of them. Okay, we don't know. You can really never say exactly what the experimental probability would be. All right, so it's got to be C or D. So the difference between the experimental and theoretical, if you have more tosses, so the more tosses you have, we know that the closer these get to each other. That's why this would be D, because the difference would get smaller between them. So that's why the answer would be D. Next, we're going to look at Venn diagrams, and hopefully you've seen Venn diagrams before. Venn diagrams visually show two or more sets as circles within the universal set, which is the rectangle. So let's see if we can interpret these Venn diagrams. A survey was conducted to find out how many high school students prefer watching comedies or action. So A is going to be the students who prefer comedies, and B is going to be the students who prefer action movies. So this 5 here would be an intersection of these two. What would that mean? That would mean there were 5 students who liked comedies and action. And what do you think the 11 represents? That would be students who don't like either of those. So, how many students like watching only comedies, but they do not like action movies? That would be all the people in this circle here, the number of people in this circle, and would this include these 5 people? No, it would not, because those would be the ones who like action movies as well. So we would say that 22 of the students like only comedies, do not like action movies. Okay, if it said how many like comedies, we would include those 5, but they also like action movies. Let's do some more to make sure we understand this before we throw some probabilities in this. This Venn diagram shows the number of classes taken by 1,500 students. Okay, so that means if I added all of these numbers up, that should add to 1,500 total students. How many students are enrolled in art? So remember, where the circles overlap would mean that there were people in both of those. For example, this 125 were in music and a foreign language. These 80 were in art and a foreign language. And the ones in the very middle would be in all 3 classes. We also have some out here who aren't taking any of them. How many are enrolled in art? So we would include all of these because even though they're in foreign language as well, we would include them. Okay, so we would find how many total people are in the art circle, and what would we get? If we add 145, 90, 80, and 200, that would tell us that 520 students total are in art. If we want to make that a percent, we would need to figure out how many that is compared to our 1,500 students. See if you could figure out what percent that would be. There were 520 students in art. It tells me that there were 1,500 total. So if you divide that, that would give you 0.347, which would be about 34.7% if we round to the nearest tenth. How many students are not taking a foreign language? By the way, do you remember what another way to ask this question would be? That would be like the complement of students taking a foreign language. So we would find all the students that are not in the foreign language circle and add all of those up. So see what you would get. That would be these people, these people, these people. Everybody that's not in the foreign language circle would be the ones not taking a foreign language, or that's like the complement, and that adds up to 970. All right, let's do another one similar to that. Looking at this, this is another Venn diagram, basically a lot like the last one. How many students chose to participate in painting? So what would that be? we would look at everybody in this painting circle. 8 plus 3 plus 2 plus 4 would be 17. So everybody in the painting circle would be included there. All right, moving on. Now we're going to look at something called intersections and something called unions. So intersections are going to be things in the middle or in the overlap of two diagrams, and unions are going to be joining the diagrams together, everything in both sets. All right, if we say the intersection, we use the word and. If we say the union, we use the word or. Intersection is denoted with this symbol right here, like an upside down U, and union is with a right side up U. So the way you can remember that is union looks like a U. The other thing that I like to remember is that and looks a little bit more like an A than the or does. Okay, so if we are looking here at this is A intersection with B, we're going to list the things that are in set A and set B. In other words, where the sets overlap, what the sets have in common. So see if you can find the intersection for sets A and B. The intersection for sets A and B would mean what is in both sets A and B. I notice they both have apples and they both have peaches. So that would be the intersection. If we did a Venn diagram, those would be the ones in the overlapping section. Okay, the union of sets A and B, that's going to be everything that is in both sets. However, we do not want to list anything twice. So we would not want to put the apples twice, and we would not want to put the peaches twice. We would only want to list them once. So what would the union of these two sets be? We would have apples, banana, oranges, grapefruit, peaches, and lemons. I would not want to list out peaches. The things in the overlapping section you do not want to list out twice. All right, let's look at an actual Venn diagram, and this says this is a universal set of parallelograms. We've got 4 congruent sides, 4 congruent angles. It says how many parallelograms fall into this category. So A and then this U, B. What does that mean? That means the union, the total number that are in set A or set B all together. They could be in A, they could be in B, they could be in both. So how many total are in sets A or B? We could do 12 plus 8 plus 6 to get that there are 26 in the union of those. Okay, next question. 2 sets are listed. What is the set for this one? So what does this mean? This means X and Y. They would have to be, the intersection means they have to be in both X and Y. Remember, this looks sort of like an and. Has to be an X and Y where they would overlap. So see if you can find the intersection. And you should notice that the -4, both of these have a -4, and both of these have a -2. So the intersection of these two sets would be -4 and -2. Okay, now let's look at this one. What is the set X and then this U, which means union. It also means or. X or Y. What would that set be? Union means we're going to list out all of the numbers in both sets, but we're not going to put anything that's in both sets, we're not going to write it twice. So let's see how many numbers are in X and Y. Okay, it goes in order from least to greatest. I've got -5. It's not in both of them. There is a 5 in both of them. I don't want to list that out twice. There's a 15 in both of them. There's a 25 in both of them. So we just want to make sure we don't list any of those twice. And the answer would be D. Those are all of the numbers in both sets. Notice they put them in order from least to greatest. Let's look at a couple more. We have a Venn diagram that shows the number of people who have purchased different types of pets. C is cats, D is dogs, F is fish. And this says how many people are in the set C and then an upside down U, D. So what does this mean? That means the intersection of C and D, or you could say the numbers that are in both C and D. So figure out which ones are in, how many total people are in C and D. The intersection of C and D would be these 3 and this 1. So all of these 4 people in the intersection of C and D, that would be cats and dogs. There were 4 people who purchased a cat and dog. Okay, which combination here represents the empty set? So meaning there would be no elements in the set. We've got children who have used a motorized scooter, manual scooter, and bicycle, and then 3 have not used any. Let's look at motor union manual bike. What would motor union manual bike mean? That would mean people who have ridden a motorbike or a manual bike, because this means or, and or means everything in both circles, so that would be a lot of people have used either or, motorbike or manual bike. Okay, what about the union of a motor or bicycle? A motorbike would be all of these people, bicycle would be all of these people, union would be everything that is in one or the other. So would that be an empty set? Is there nobody that is in a motorcycle or bicycle? Yes, there would be all these people and all of these people. That is the union of them. Okay? Motor that is intersected with manual. So anybody who have a motor and manual, is that an empty set? No, there's 24 people that are in the intersection of a motorbike and a manual bike, so that is not empty. And what about the intersection of a motorbike and a bicycle? How many people have ever used a motorbike and a bicycle? We have this many have used a motorbike and this many have used a bicycle, but these don't overlap, so there is no intersection between a motorbike and bicycle. All right, let's look at this. This stuff doesn't really matter. How many elements are in the complement of T intersected with P? So T or P. First of all, let's figure out what T or P, where that would be in this Venn diagram. So how many people are in the set T and P? T and P would be these 3 people, the intersection of the 2 circles. The complement is everything that is not part of this. Everything that is not part of this. Okay, so let's figure out what the complement would be. These people, and these people. So how many people are in the complement of T intersected with P? That would be 42 people. So if you add the 42 people and you add these 3 people, that should be your total amount of people. So complement is everything that's not right here. And next, use the numbers 1 through 20 as a sample space, so that means possible outcomes, for the sets of numbers described below. X is going to be a set of multiples of 3 between 1 and 20. So we're going to list out the multiples of 3. Y, we're going to list out the multiples of 4. So X is listing out 3, 6, 9, 12, 15, and 18. I believe those are all of the multiples of 3 between 1 and 20. What are all of the multiples of 4 between 1 and 20? That would be 4, 8, 12, 16, and 20. And factors of 4, what are those? Those means numbers that can multiply to get 4 between 1 and 20. So the factors of 4 are numbers that can divide into 4 evenly. That would be 1 can go into 4 evenly. 2, can 3 go into 4 evenly? No. 4 can go into 4 evenly. And obviously no number is bigger than that. See if you can figure out which statement is true. Letter A, the union of X and Z is the empty set, meaning there is nothing in the union, and that's not true. Union means we would list out all of these numbers and all of these numbers, and they don't have any overlap, I notice. But so this would be true. The intersection of these would be an empty set, but the union, everything that's in this one or this one would be listed. The intersection of Y and Z means things that are in both Y and Z. And I noticed the intersection for Y and Z, the only thing they have in common is 4. So that would not be true either because the intersection would only be 4. This might be the union. Letter C, the union of X and Y, that means everything in X or everything in Y is included. That means we would list out all of these numbers and all of these numbers, but we would not write any duplicates twice. So I know they both have a 12. I believe that's the only number they both have in common. So we would list out all of these numbers, 3, they did 3, 4, 6, 8, 9, 12, 15, 16, 18, and 20. That's all of them. So that's everything in both sets X and Y, but we don't write the 12 twice because we've already listed it. And letter D, the intersection of X, Y, and Z, that would mean where all 3 of them intersect. That would mean a number that is in all 3 of these. And there is no number that is in all 3 of these sets. So that would be the empty set.